now a better understanding of how Python works. And the one thing that you should have taken away from your previous lessons in Python is that we need these packages to help support whatever work we're doing, may it be solving a math problem, creating a plot, doing some type of data analysis, or even just combining all these elements to write up results and your understanding of a particular data set or something that you observed. So in today's presentation, I'm going to cover three key packages that we use that we need to know as astronomers. I have included a fourth package as well, but depending on the time, I may or may not get to it, but I will send you the material so you can go through it and get an understanding. Okay. Oh,
Should be able to do it
uh,
now.
okay. Okay. Um,
Looks great. We can see the slides.
cool. All right, so yes, so first I'm going to talk about NumPy and pandas. NumPy is for anything that has numbers in it. It can be a matrix, it can be an array of numbers, it could even be images, because when images are being processed through Python, they come in as these matrices, these 3D matrices, which have X and Y positions and a value assigned to it to give it its pixel count. And pandas are huge data tables. I will get into a little bit more. So in this first part of the presentation, I'm going to talk about what NumPy is, what NumPy arrays are, how we can index through those arrays and filter out those arrays, how we can do math on those arrays, how we can do some statistical operations on those arrays. And then I'm going to talk a little bit about pandas and how to read and filter through a pandas data frame or a catalog. Okay, so NumPy is a very elegant package that a lot of other packages also use, which is the examples that I've given on the right. In NumPy, the basic data type is ND array. It gives you a grid of numbers that and all of one type, and you can do math on all of them at once. Anytime you open an astronomical image or you open a astronomical data set, it could be a spreadsheet type of a data set, for example. Every time you open that, it either comes by default in a NumPy type of a grid set, or you can easily convert it into a NumPy type of a grid, or you can easily convert it into a NumPy type of a grid set. And the reason we do this, it is a very standardized operation. Everybody uses NumPy, and it becomes really easy to do any kind of math or any kind of data extraction from these grids. To install NumPy, if you install Anaconda or Conda, NumPy should come with it because it is a very basic package. But if you install Python from scratch through terminal, you may have to pip install NumPy separately. So pip install is to install NumPy from PyPy, which is this universal library of, or I guess this universal database of all Python libraries. So you pip install NumPy, or assuming NumPy is already available, then you can import it in your Python script as import NumPy as NP. Now this is called aliasing, where instead of having to call the package over and over again by its actual name, it can be clunky. It's a short name, but it's not that short. So you can alias it and call it something really short like NP, or you can call it whatever you want. NP is a standard everyone uses. And it is best to stick to these conventions for very well-known libraries, because if you send your script to someone else or you're collaborating with someone else on your Python notebook, then it just becomes easier for them to understand what you're doing. When they say NP, they know that you're doing a NumPy operation. So yeah. So the other reason you want to use NumPy instead of using just native Python, I wouldn't necessarily call them packages, more like native Python operations on numbers, is because every time you have to operate through a list of numbers, let's say, you would probably have to run a for or an if loop over it, and that can take a lot of time, somewhere between seconds to minutes. Whereas if you parse that grid through NumPy, that whole operation would be 1,000 times faster. That's another reason you want to use NumPy. Okay, so in NumPy, we call a grid of our numbers an array. An array can be however big and how many ever dimensions you want. So the most important things you need to know about an array are its shape, its type, and size. So np.zeros is an example over here. That is one way to make an array that is all zeros. Now, the three attributes that these arrays that I described, one is shape. It tells you the dimensions of your array. So this is a 5 by 5 array. It has 5 rows and 5 columns. D-type tells you the data type of the numbers in that array. It's float 64, which is the default data type of all numbers in NumPy array. But if you want to save space, you can go to float 32. You can also have integers instead of floats if you know that you're not going to use a decimal point ever. The other thing is size. Size tells you the number of elements in that array. So yeah, over here I've given you the examples. Shape is how big it's in each dimension. D type or data type is what kind of a number it is. So float 64 is a basic, int 16 is just integers. Bool is if it is a true and false array. So you have an array that just goes true, 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 false, false, false. That is a Boolean type. Um, so one way to make arrays is the way I've shown here. If you need an array that's all zeros, sometimes you need to, sometimes you need to make a matrix that is all zeros to support a certain kind of operation. So you don't have to create a whole list of zeros and convert that to an array. You can just do np.zeros. The same thing, instead of zeros, if you want ones, it's just np.ones. Then maybe you want to create arrays that go between point A and point B and has these many elements, or it goes from point A to point B and you need to skip count by these many elements. You use np.arange and np.linspace for that. np.linspace is start point. In np.linspace, you define start point, end point, and the number of elements between start and end point. So here I'm creating a 1D array that goes from 1 to 2.5 and has 100 elements in total. In np.arange, I go from 0 to 10, but I skip count 2. So I just get every second element. I go 0, 2, 4, 6, 8, and so on. Now, the example that I've given over here of fits. So in my previous slide, I mentioned that different scientific packages that especially we as astronomers are going to use, they all have NumPy as a base because they also process data sets through the NumPy package. So for example, in a FITS file is the default file format in which you get your data from telescopes, let's say. And when you read out your image, let's say you have a file called image.fits and you're reading out your data from it using fits.getData. I will explain this when I talk about Astropy. The default data type that comes out of this is a NumPy array. And within the NumPy array, the numbers are usually float 64, unless the fits file was written in any weird fashion. Oh, the other thing that I forgot to show is, so if you've, in your earlier Python lesson, you must have seen a way to do lists. So let's say I want to define a list that is A equals and a square bracket list, 1, 2, 3, 4. I can also convert a list into an array. I just need to use the function np.array, np.array, and put whatever list in it, and then that is converted into an array. That way I can do whatever math operations I want on it and use it with other NumPy arrays if I need to. Now, how to index through these arrays? By indexing, I mean how to pick out an element, how to arrange these elements. So this is an example of a NumPy array, np.arange 2025. So np.arange 25 just means I want to have an array that is the first 25 numbers from starting from 0. So it goes 0 to 24. Dot reshape. Now you can, even if you define an array in a certain format, in this case I defined a 1D array, I can reshape it into how many ever rows and how many ever columns I want. Reshape 5 by 5 just reshapes into a 5 by 5 grid. And this is what my grid looks like. The first row has 0 to 4, the next one has 5 to 9, so on and so forth until I have up until 24. Just a reminder, we end in 24 here because Python indexes by 0. So Python starts counting from 0 and goes to 24, and that is 25 elements. That is the 25 in np.arange. So this is a tiny 5 by 5 image. You can think of it that way. So if I want to pick the very first element, just the very first pixel of that image, I would do 0, 0. The 0th element, the 0th row, 0th column. It gives me the 0th element. Now, if I want to pick out, do a 3 by 3 cutout, in this case, at the very center of the image, this is the number I give it, 1 to 4, 1 to 4. 1 to 4 means I go from the first row to the fourth row, first row to the third row, and first row to the third column. This number here. So when you're indexing in Python, typically, when you go from one range to another, the colon basically. It means the colon means everything up to but not including. So 1 to 4 means everything from 1 up to but not including 4. So this is 1 to 4, 1 to 4, a 3 by 3 cutout. Now, if I want to select a whole column, this is the operation that I would give it, where the colon means everything, comma means I'm going into the next dimension. So every row, but only the second column, which means I need the second column. Now, if I need to select everything in the second row, I would do image 2, comma, colon, meaning the second row and everything in it. The one caveat that you need to notice is whenever you pick out pixels like this by position, whenever you take slices, maybe a 3 by 3 cutout, a single pixel, or a whole column, it does not create a copy. So if I accidentally or intentionally change anything in this slice, so if I do image if I select this image and put it equal to a different 3 by 3 number. So right now it is 6, 7, 8, 11, 12, 13, 16, 17, 18. And I select this and I say this equals some other matrix. I don't have a backup copy, so I'm going to be changing everything in the original array. This way you can manipulate and change your images, but if you do not intend to do that, you should first make a copy by doing dot copy. So this is picking out pixels by position. This is useful if you can see your image, if you can see your data set, and you want to pick out just different parts of it visually. The other way of picking out pixels is by value. This is what we call masking, where we give different conditions and we select or deselect parts of our array. So for example, let's say when you take an image using a normal detector, no detector is perfect. Every detector is what we call bad pixels or hot pixels, where those pixels are already saturated during the manufacturing process or overused. They just got saturated that there is no meaningful signal on them. So I know what values those pixels have. So let's say in my case, this is my detector, and I know all those bad pixels have a value of over 18. So I first create a statement, hot equals image greater than 18, where I am giving it a condition saying whatever that hot pixels are whatever is in my image that has a value of over 18. This creates a Boolean array, an array of true or false. So remember, as I mentioned earlier, as a NumPy array can have any data type. We can have floats, ints, or bools. Bools are true and false arrays. This creates a true or false array. So hot is going to have the same size. It is still going to be a 5 by 5 array, but instead of going from 0 to 24, it's going to be false, 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 false. But as soon as it goes over 18, it's going to be true, 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 true. This way, instead of having to loop through using if statements and for loops, instead of having to go through individually every single image, you can select chunks of data at a time. Now that I've defined my array, my Boolean array of which is a hot pixel, which is not, I can use it to select or overwrite. So maybe I want to just flag them, or maybe I just want to completely delete them, just remove any value associated with it so that when I plot it, it just shows up as white or it doesn't do any math. So if I do image bracket hot, that way I'm selecting everything that follows this condition, everything in my image that has a value of over 18. And that is the boxes that are highlighted. Now I can give it whatever value I want. np.nan means nan is basically an equivalent of infinite. It is anything infinite or anything that is non-applicable or non-valid. So these don't have any meaningful numbers. It is just nan, so it does not do any operation whatsoever. Do not give them 0 because 0 is a number with a value. So anytime you want to give something that has a position, you want it to be retained in that position, but you just want to have it a dummy meaningless value, give it np.nan. So that is about picking out pixels by position or by value. If you want to pick out a row or column visually, or if you want to mask out based on some information you have about their values. The next thing is to do math on these things. So if you want to do math between two arrays, I call one image, I call the other one dark. Image is used scientific image. Dark is usually an imagery detector with no light. We use that to subtract any background noise due to the detector. If I do image minus dark, I need to make sure both image and both dark have the same array sizes. So in this case, my image was a 5x5 array, a 5x5 grid. So dark also has to be a 5x5 grid. And when I do image minus dark, every pixel in image is the operation goes a pixel in image minus a pixel in dark. And it has to be the pixel in the same position. So if I go back to my image, so if I have, let's say my dark, for simplicity's sake, is a 5x5 grid with all zeros. So image minus dark is going to be 0 minus the 0 in the dark, 1 minus the equivalent position, the equivalent pixel in the first row, second column. So in this case, 0, then 2 minus 0, so on and so forth. And the result is also going to be a 5x5 array. If I do division, it's going to be the same thing. Now, if I do numbers like this, so image times 2 plus 100, the times 2 plus 100 would apply to every single element of my array. And I can do something more complicated, like, logarithmic operations. This I do to convert from flux to max. This is a whole other thing. In astronomy, we can go into detail in a later talk if we need. And there are other usual functions as well. np.sqrt is square root. np.exp is exponent. Log 10 is log to the base 10. You have your trig functions. np.abs is the absolute value, so it takes everything and gives you a positive number. np.round is to round up your numbers or round down, depending on the decimal value. These are called ufuncs. These are these universal functions that are applicable to any NumPy array whatsoever. Now, the other thing you can do is broadcasting, where you can mix up shapes. So let's say when I'm doing image minus dark, for example, my dark is a smaller size than my image array. So what if you want to do the operations? What if you want to stretch out the smaller array to match the size of the larger array? NumPy can do that for you. You don't have to write a loop from scratch. So for example, so the one way you can do without stretching is if I want to do a subtraction, if I want to do an arithmetic operation using one number, but on every element, so image minus 100, for example, I don't have to create an array that is the same size image with every element being 100. Image minus 100 would just do that for me. Image minus 100 would subtract 100 from every element in image. Now, let's say I have a data cube and I have sky, but then I just want to select one sky value per frame of a data cube, or data cube might be a complicated idea. Let's say I have a 3D matrix of a sky. I have a all right, I have a 3D matrix of an image, a 2D matrix of a sky. I need to add one more column, or if my sky is one dimensional for some reason, I need to add two more dimensions to it to match cube. Doing this would give me one sky value per frame of a data cube. That way I am so we also call this padding, where we add dimensions without affecting the actual data. And NumPy lets you do that. If I was going to use a list, or if I was just using a list of numbers, then I would have to do that manually by myself using for loops, and that can take a lot of time. So yeah, by this point, you can already appreciate how easy it is to index through, to mask values, and to do math on NumPy arrays. The other thing is to do statistics. You can do your mean, median, mode, that kind of things on your data set. But the one thing that you need to be wary of is axes. Because in most cases, in real life, when you do NumPy operations, we're doing it on 2D grids or more, 3D grids, 4D grids, 5D grids. So what if I want to do statistics on only one row or one column or on all of it. So I can do, so for example, this is my new image. This is my new image, we call it D, just for simplicity's sake. If I did d.min or np.mean, so for doing statistics, you can either do dot median dot mode, or you can do np.mean so and so, np.mean brackets d, np.median, np.mode. If I did np.mean or d.mean on this whole grid, it's going to give me the mean of all the 12 numbers that you see here. But usually when I'm doing statistics, I want to squash my numbers along one axis, which is why we define this axis keyword. So d.mean axis equal to 0 is going to squash everything along the 0th axis. So I can get, so if I have, if I'm looking at 4 stars and each star has 3 different images, I am squashing along the exposures. So I should get a mean, an average value for each star. So, which is a meaningful estimate. I have 3 exposures for 4 stars. X is equal to 0 would give me the average value for the average exposure for each star. Now, if I want to squish the stars and get the means for each exposure, then I would squish along X is equal to 0. So I would get 3 numbers in this case, 1 number for each exposure. And d.mean, it squashes everything. The axis that we name is the one that disappears because we are doing our statistical analysis along that axis. And it's not just statistics. It's also for any such function that can be applied to a grid, like sum, standard deviation, max, min, all of those things. So that's everything about NumPy. If you have any questions, put it in the chat and I will address it after I talk about pandas and Astropy. So this hopefully has built an appreciation of why it is super important to use a very flexible mathematical package. Pandas is to process large data sets through tables. We call these tables data frames. A data frame is a table with named columns and typed rows. So for example, let's say I have a targets.csv file, which has a list of all the targets that I'm going to observe with all their details. I can read it using pd.read_rsv. So first I have to import pandas as pd or pip install it if it doesn't exist already. Same rule for aliasing. PD is a convention that everyone uses, so better to stick with that. And dot read CSV reads a CSV file. If I do dot head, it would automatically select the first 5 rows. Now, if I know that my header row, which tells me all the table names, is just the first row, we would need to define it. Cat.columns will actually extract every individual column from my pandas data frame. Dot describe is like the things that Excel or Google Sheets shows you at the very bottom, where it tells you the number of things in each column, the mean of each column, the max, min, that kind of stuff. Just to give you an overall picture of what every part of your data frame is like. You can also do masking in this. You can also do masking and filtering just like we did with NumPy. But in this case, it's easier because you don't have to blindly think about values or pixel positions. Here you can use your column names. So this is a sample data set that I have. I've kind of inspired it from the things that I'm working on. So if I want to select, let's say, all K-mags, all I need to do is cat brackets and define the keyword that I'm selecting. In this case, K-mag. I can also define 2 columns. And if I still want to use numbered positions, like the first row, for example, then I do .iloc, which is the item location. 0 gives me the first row, which is this row. I can also use conditions where, let's say, if I want to select something of a magnitude less than 7, I would do this. So when I do this, the bright rows that will be selected are these 2 because they have a magnitude less than 7. Let's say I want to select things by position. So I can use the deck column, I can use the RA column, and that way I filter out things within my observable range, for example. I can also group by, I can also sort based on a row and column. So basically, Pandas is a way to tackle spreadsheets in a Python format. If you haven't used it yet, it still might be easier to use spreadsheets, but I would advise you to use a spreadsheet along with the pandas functionality on Python to help you figure out how you can make your spreadsheet experience more optimal and more translatable to other Python functions. So this is your assignment. I will send it to you a little bit later, but basically I want you to, I have three things for you to do. One is to make hot pixels out of a fake image. And that way I'm also going to make you look at different NumPy functions that I haven't discussed before, and then to use the tag catalog to pull observable targets. I will be sending the catalog as well, so you can do this homework. So I hope this is what you learned from this section. I know I'm a little over time, so I'm going to quickly speed through Astropy so you have a real example of an astronomy package that everybody uses. Okay, let's see. All right. I have in this slide, I have Astropy and Scipy. I'm going to skip Scipy, but still send you the information so that you have it and you can explore it as and when you have the time. So what is Astropy? It's a Python package that offers tools and functions that are useful for various tasks in astronomy. You can use it to plan an observation, to do your observations, to reduce or process the data from your observations, analyze it, and other numerical and modeling tasks. So Astropy usually comes with Anaconda installs, but if you don't have it, you can just do pip install Astropy. If you want to update it, you can do conda update Astropy. And yes, you have Astropy, and then you can just do import Astropy. But import Astropy is not super easy, is not super straightforward to do because unlike NumPy and Pandas, where it's one library with many functions, Astropy is like one giant meta library with so many sub-libraries, and in most cases, we don't need all those sub-libraries at once. So people using Astropy typically just import the specific sub-library they want and just go along with it. So this is a format that we follow. We do from Astropy import subpackage or import astropy.subpackage as whatever initially you want to give it. Or if you want to import just one tiny functionality, a class from a subpackage, you can do from astropy.subpackage, import the class. Because this way you can reduce the space you're taking and the processing time you're taking and just import what you really need. So these are examples of subpackages. You have things like units and constants. Units are very great because instead of you having to type in conversion numbers, if you do dot meter times dot kilometer or whatever, it would do the conversion math for you. Constants contains a number of physical constants that are useful in astronomy. Coordinates are classes that help you define things like right ascension and declination, which is a coordinate system that we use to define positions of objects on the sky. Then you have other coordinated packages, which are app packages separate from Astropy, but you can use them with Astropy to make your observing planning or data reduction a lot easier. AstroQuery, ccdproc, FOATutils are examples of that. Okay, so the next thing, quantities. So in quantities, I'm going to talk to you, give you a bit of better, deeper understanding of how units and constants work. So import astropy.units as U imports the units library, which is helpful while handling and calculating using different quantities with different units. So for example, I want to calculate velocity. So I want to divide meter per second. Now these two are different units, but Astropy knows how to handle them and what value to give you in the end. So Q dot value gives me the specific value. Unit gives me the unit, meter per second. Now, parsec is a very commonly used measure of distance in astronomy. So if I do 1 times u dot parsec, so 1 times u dot any unit will make that number, it will take it from being a simple float, a simple number, into an actual physical quantity. So in this case, x is now a distance quantity with the unit parsec. If I dot 2 and whatever unit, I can convert units easily. So this gives me the parsec to kilometer conversion. 1 parsec is equal to 3 times 10 to the 13 kilometers. And x is now of the data type quantity and no longer a float 64. Constants is a library of constants. Instead of you having to define these constants, you can just pull it from this library and it makes your life easier. And they also come pre-packaged with units, so you don't have to worry about that. So C.G, the universal gravitational constant, if you print that, you will get all the details of it. the gravitational constant, the value, uncertainty units, everything. So this is a quick assignment that I have for you. Basically, I want you to do a simple physics problem of calculating the force, the gravitational force between a star that is 3 solar masses and a planet that is 10 Jupiter masses 2 AU away. I will send you the assignment and you can figure it out. This is the answer to just to give you a quick look. Now, the other thing that we really do in Astropy is input and output. We have the FITS files that I mentioned to you earlier are an example of inputs. You have these images that are encoded in a special way, and because the special way is standard across all of astronomy, the input and output packages help you handle that. So one such input output package is table. It kind of works like your pandas data frame. I would like to think astropy.table was based on pandas, and this helps you read things from a table and write things to a table. The other one, which is very commonly used, is FITS. FITS is a data format that is used for transporting, analyzing, and archiving scientific data files. It's not just an image format like JPEG or GIF because you store more than just an image. You store scientific data into it. Part of the scientific data are images. The other part of it are rows and columns of information about that image. This is usually what a FITS image looks like. You have a primary array, which is the actual image that you're interested in, and it also has header data, and then you have image extensions. So you usually have a header unit and a data unit. So we do from astropy.io import fits. IO is the input output module of Astropy. So this is an example I said where you can import just one class out of a subpackage. The subpackage here is IO, fits is a class. Fits is a gigantic class. So if you're only doing reading, opening, closing fits data, this is all you really need. This assignment is to test the exact Astropy install you have. This is a very standard operation. Every Astropy install comes with a test0.fits file. That way you can actually just play around and try to get an understanding of what a fits file is like. The last thing you can do is planning observations. Well, not the last thing. One of the things you can do is planning observations. Um, and for that, Astropy has these coordinates packages where it gives you the location, which can help you define the location from where you're observing. Sky coordinates, the coordinates of the thing that you're observing. All TAS basically kind of converts those RA and deck coordinates into something more physical you can see, altitude and azimuth. Now, this is an assignment that I will send you in its entirety with its answer and all of that so that you can better appreciate how astronomers spend time to plan out their observing runs. I think that's all I have for Astropy, and I'm so sorry for going over time. I will send these slides so you can go through them very carefully and you can ask me any questions that you have.
Thank you so much, Maria. Any questions? Feel free to unmute yourself or type in the chat.
Or yeah, we can also go to the next presentation. And if you have questions on both our presentations, you can eventually put them in chat and we will address it at the end of the session.
That sounds good. Maybe in the interest of time, let's move on to the second presentation by Grace. Thank you, Maria.
Hi, can you guys hear me?
Yes.
Okay, cool then. Yeah, so hi guys, I'm Grace. I am currently a master's degree student with my research focus on stellar astrophysics currently. So I am gonna start with TESS. I think most of you guys must have heard about it. So this presentation is gonna be about like how you would be extracting light curves and all, okay? So let me start sharing my screen. Okay,
Looks good. Go ahead.
Okay, I guess you all can see my screen, right?
Yeah, we can see it, but we are seeing the
Yeah.
email page now.
Okay. Okay. So let me start it out. So I guess like you guys must have seen all this beautiful night starry
Grace, we
sky,
are seeing
right?
your Gmail inbox, not the presentation.
Okay. Okay, can you guys see it now?
Yes, go ahead.
Oh yeah, I'm so sorry for that. Okay, so yeah, let me start that. Okay, guys, so you guys must have seen a beautiful night starry sky all the time. So what you can see here is, like a lot of stars and a beautiful sky. But what if I tell you that you can actually see a invisible planet here, and how cool it would be that you're identifying that. So that is the whole mission here. So before we start, I wanted to tell you guys one thing that I hope that you all love to, be in a detective role and everything. So we're gonna be doing a lot of digging and investigation here. So for that, I would like you to guys to meet someone called Tess. So as you all know, the detective Tess is Transiting Exoplanet Survey satellite who was from NASA. So TESS was launched by NASA in 2018 with just one mission given, that is finding worlds where no one has ever been before. Like days after day, orbit after orbit, TESS watches the stars, but not just with curiosity, but with a lot of patience because somewhere hidden a planet that no one ever have found. So that is what we're gonna do. So let me tell you guys a small thing how we gonna handle this mission. Okay, so our mission will consist of a 7 stages. Okay, so step one, we will be identifying a star. So when I say identify a star, instead of looking for a planet, we gonna look out these stars. So you know that every planet orbits around a star, like how our Earth orbit around the sun. Likewise, every other planet does that too. So instead of looking for a planet, we are watching the star, okay? And then we gonna measure its light, okay? So when I say we, it's gonna be Tess. Tess measures the amount of light coming from the star, and this is called its brightness or flex. Okay, like I would say in a simple words that imagine checking the brightness of a light bulb every few minutes. We're gonna do it in the same way. We're gonna check out the brightness of a star every few minutes. Okay, and then watch it over the time. So you will be not, like it's not enough that having just one single measurement. So Tess is going to keep measuring the star's brightness again and again for like days, weeks, and everything. So by the time, like with the like a lot of time, we would be end up with two important things, that is brightness and time. So test is basically is a data where you can see like brightness versus time. I would say it in that way. Okay. So once we got this data, we are going to draw the evidence and we're gonna plot the brightest measurement on a graph. And now that's our graph called a light curve. Okay, so this light curve, okay, it shows the how the star's brightness changes over the time. You can see here, like the light curve is, it's not like a perfect sine curve, or it's not like a really a perfect curve, right? So you can see like, tiny dips and ups and downs and everything. So that is the major thing that we will be focusing here. All the tiny dips, it could be a planet that passes in front of a star, and while passing, it blocks a tiny fraction of star's light. The light curve suddenly dips for a very short amount of time, and that dip is our biggest clue. Okay, so that is how we're going to solve this mystery. So if the dip repeats at regular intervals, we found a strongest evidence that a planet is orbiting the stars. And that's how, congrats to you guys that you guys discovered a exoplanet. So now I'm gonna show you guys like how does in actual real time it is gonna work. Okay, yes. So I'm gonna show today I will be using Jupyter, but you guys can even use it through Google Colab. That is like if you're like starting out as a beginner, I would totally suggest you guys to use Google Colab, but Jupyter is also fine. So I'll be using Jupyter today. Okay, so yeah, I don't want to take up so much time, so I did like everything in the before, and I'll explain you guys like every single stages. Before that, can you just tell me like I'm sharing the notebook file, right?
Yes.
Okay, perfect. Thank you. Okay, so let's start with the code. Okay, so. So as I gave you guys already the game plan, okay? The stage one, we are going to look at the stars, and the stage two is, like find what is the, like how the light curve works, and then we're gonna drop out like where the planet is orbiting. We're gonna do it in that way. Okay, so yes, most exoplanets are far too small and too close to their stars to be seen directly. So instead, astronomers look for indirect evidence. Okay, one of the most successful methods is transit method. So whenever a planet passes in front of a star, it blocks a tiny fraction of the star's light. That means the star just a little dimmer for a short time. If this happens repeatedly, we know something that is Earth is orbiting the star. Okay, so yeah, let me start with like in your real-time example. Okay, so yes, so let me start with okay. So first you have to import this package called Lightcurve. So you just import it, and then next we have something. This is gonna be our toolbox. Okay, so like how a magnifying glass for Sherlock, like that, this particular toolbox is for us. So, like Maria has already explained to you guys about like what is Numpy, Matplotlib, Lightcurve, Astropy. I'm just gonna give you a little, like a little brief about it. So let's start with Numpy. Numpy helps with a large amount of numerical data. A telescope doesn't produce 10 measurements, it produces like thousands or even millions. NumPy allows Python to work efficiently with these numbers. And the next we have is matplotlib. So let's say, suppose NASA gave us a spreadsheet containing 50,000 brightness values. Could we understand by simply reading the numbers? Probably not. Matplotlib converts those numbers into graphs, and astronomers often understand data better through visualization than through the stars. And then we have Astropy. So Astropy is a very standard astronomy package for Python. It understands the astronomical units like days, parsecs, astronomical units, solar masses, and like so and so. Instead of treating the like using it as a plain numbers, it remembers the actual physical value of these numbers. Okay, and then light curve, that is the important package that through this light curve package we gonna communicate with NASA's archive. Okay, so first thing you have to we are going to do is search the light curve. Okay, so today I am going to be looking light curves of Pyman CC. So yes, so you can see here first I made a light curve underscore search underscore light curve, and I'm gonna mention like what star or like what part I'm gonna be looking over that. And then next you can see the mission. I'm gonna name it as TESS, like since we are using TESS. And the next thing that you can see here says author equals SPOC. Okay, so SPOC, which stands for Science Processing Operations Center. what does it exactly mean? Why do we use SPOC? Okay, the telescope when first records the raw observations, okay, and then it sends to NASA. NASA processes those observations to remove the instrumental effects, like all the known instrumental effects. The process data are generally much easier for astronomers to analyze. Okay, so once we did that, okay, we would be getting the a catalog of the available data under the particular star that we look for. And then next, and the next you got to do is download your data, and that is this particular function called. And then after downloading, you are going to plot it. Okay, so this is a light curve plot, I can say that. So guys, let's talk about something about this like this output. Okay, remember I have already told that TESS is basically the differences of brightness versus time. So brightness or flex versus time. So the time is in our x-axis and the brightness is in the y-axis. Okay, so and then you can see here that the time, next to the time, it mentions something called BTJD, which is barycentric test Julian date. So, which is basically like we have our own calendars. It's the same way that TESS has its own Julian calendar. It is basically that, okay? And you can see that like there is a gap in this whole a vertical gap you can see in this output, right? Do you guys, by any chance, do anyone has any idea about like what is the reason for the gap? Is there any particular reason? Do you guys have any idea? Okay, in case if you don't, that's no worries. Let me tell you guys. So that particular gap can insist a lot of stuffs. It could be look, TESS can catch a break. The TESS was particularly not looking at that star on that particular time, or it could be even any issue with the spacecraft or something like that. That is a reason the presence of the gap over there. Okay. So now we got our light curve. Okay, so what do we do next? Now, after we downloaded the light curve and then we plotted it out, and what we gonna do? So here comes the real astronomer work. Okay, so after we get the data, we gonna clean it. So this function, you basically select the brightness and you're gonna clean it. Okay, so this is what you can see here, okay? The data that we had, and we're gonna clean it here. And after cleaning, this is how we get it, okay? Now it's all scattered plot, right? So after this particular thing, after this cleaning of the data, we gonna look into our planet. So we will be finding out like how the planet is gonna be. Okay, so here is the interesting part. Okay, yes, we are done with the light curve, and let's start with the searching for a planet. Okay, so in order to search for a planet, this is where the step a computer is like becoming very essential part. Okay, imagine examining a 50,000 measurements manually to take a lot of hours, right? So instead of that, we're gonna use an algorithm called BLS. Okay, so BLS, which is basically called as box least squares. Why is it called box least squares? Okay, the reason is the brightness suddenly drops, and then it stays low briefly and then bounce back, and then this like this going on, like lowing and up, coming up. This whole thing resembles like a box, and that's the reason it's called box least algorithm. So this algorithm tests thousands of possible orbital periods, like days, 2 days, 3 days, 4, 5, until it finds the period where the dips repeat most consistently. Okay, so and this diagram is called as periodogram. This, like unlike a light curve, it does not show you the brightness. Instead, it shows how confident the computer is representing the signal exists. The tallest peak corresponds to the most likely orbital period. Okay, and then we're gonna find now that we have a proof that there is a planet orbiting this particular star, and let's see how long the planet takes to orbit. Okay, so for our planet it takes 6.2 days, that to complete an entire orbital period. Okay, and once you found it, okay, next comes the like the transit part. So here, this one tells us, like when one particular transit occurred, and once we know both the orbital period and the first transit, we can predict every future transit. Okay, so after that, we're gonna do something called folding the light curve. This is one of the cleverest idea in astronomy, I would say. Suppose let's take our planet, like planet passes every 6 days. Instead of viewing 6 months of observation, we cut the data into 6 day pieces and stack them on top of another. So it's basically, like stacking of, like each data. Okay, so by stacking, now we have every transit lines up. The planet suddenly becomes like very easier to see. Okay, so once we got this, then we have the important part, that is a test object of interest. Okay, so this is called as a test object of interest. Okay, so before that, let me show you guys something. Okay, so based on the periodogram, you can, like when you adjust, and you can basically see what is the flux and how the, like the, how does the orbital period works and everything. You can see it, like in this way. Okay, then let me show you the next part, that is test object of interest. Okay. Okay, so you see here there are like a little tiny blue dots that you're seeing on this graph. So each blue dot represents one planet candidate that was discovered by TESS. The horizontal axis is about the orbital period, and the vertical axis is for the planet's size. So why do you think most planets appears in the bottom left? Do you guys have like any idea? If not, it's fine. I'll just let you guys know. The larger planets block more light, making them easier to detect. Planets with short orbital period transits, move frequently. So test observers multiple, like observes multiple transits while watching the same region of the sky. So this is an example of observational bias. This graph shows what tests find most easily, not necessarily what is most common in the universe. So now I would like to conclude with, like today we followed exactly the same workflow that is used by many astronomers. We access real NASA observations. We measure the star's brightness, clean the data, search for repeating signals using BLS algorithm. We folded the light curve to reveal a transit, and finally we compared our results with NASA's catalog of planet candidates. So this is not just a simple Python exercise. It's like a example of like how modern astronomy is done. Every new telescope sends back enormous amount of data. Astronomers combine physics, maths, and programming to turn these measurements into scientific discoveries. So you have completed the first step for the same process. Let me know if you guys have any questions.